All right, so since I'm in gearing for golf, we need to finish up our notes for section one here for biology. We're just covering these last two objectives in this video. We're going to talk about how ions form, and we're going to compare ionic and covalent bonding. So, some classes left off a little bit after this, but I know at least one class still needed a definition for compound. So we'll pick that up real quick. It's a substance made of atoms of different elements bonded together in a certain ratio. So some good examples of a compound would be things like water or sodium chloride, right? Or even possibly carbon dioxide. So when they talk about a certain ratio, understand that it does matter that there's two hydrogens and an oxygen in water, because if there were two hydrogens and two oxygens, it's a completely different substance. That's now hydrogen peroxide, right? So that 2-to-1 or 2-to-2 ratio matter. Sodium chloride is an ionic compound, right? And that sodium has a +1 charge versus the chloride's negative charge, so it's a 1-to-1 ratio. But if I add something like a magnesium that has a +2 charge, it might take two chlorides to balance that out. Right? So that ratio, again, is a factor. Carbon dioxide has two oxygens. You guys should recognize this compound as carbon monoxide, right? You might have a carbon monoxide detector in your basement. You should if you have a gas furnace. Right? You should have one of those just in case, because it's odorless, colorless, toxic, right? Extremely toxic. It irreversibly binds with your hemoglobin, so you can't get oxygen to your cells. So that ratio does matter, right? And it's emphasized in these examples. So knowing whether it's two hydrogens, one oxygen, or two oxygens to two hydrogens, that does make a difference. Which brings us to our ion definition. This is an atom that has gained or lost one or more electron. So what we're talking about typically with ions is you have a metal, like sodium, that happens to be in group 1, group 1A, meaning it has one valence electron. I know you guys have used these Lewis structures before in the past, so I'm just going to continue with those. I put one dot around sodium, it means it has one valence electron. Versus that chloride, that chlorine originally, being in group 7A, it has 7 valence electrons. Right? And I don't know how in-depth you guys went into ionic bonding and the formation of ions in your physical science. But essentially, we're just trying to follow this octet rule, and you want to have 8 electrons in that outermost shell, in most cases, unless it's hydrogen. But sodium and chlorine, right, are both going to achieve that in different ways. And in order for sodium to achieve stability, it actually wants to lose an electron. It wants to lose that single electron it has in its outermost shell, because then you can go to an inner shell that's actually full and it's going to be more stable. Whereas chlorine is going to want to gain that electron lost by sodium, because now it has 8 valence electrons and it's happy, it's full, right? So they want to get that octet rule so that they can be stable, so that they can be happy. Right, this chloride ion now has a negative charge because it gained an electron. The positive goes with the sodium that lost an electron to make this happen. So then that ionic bond is the attraction between my sodium and my chlorine at the end of the day. My sodium and now my chloride ion are attracted to each other with what's called an ionic bond. Right, so this dotted line of attraction between the two is that ionic bond. Your definition for an ionic bond is just that attraction between negative and positively charged ions. Let's say ions down there. is just cut off a little bit. So now that we have ions in play, we have one more step to our counting atoms series. So we did practice with a few of these in class already. Right? You should already have a basic understanding of what you need to do. So again, always, I have a nuclide. I have this calcium 40. And I need to look up some information off the periodic table. Calcium is number 20 on the periodic table. And using this information, using the shorthand, which you have to give me all three things here. You'd have to give me that symbol, that mass number, that atomic number. On the worksheet you're going to do in class today, you have to give me those things or you don't get full credit for your problems that you do. But once you have this, you should be able to tell me how many protons, how many neutrons, and how many electrons are in this atom. So far we've done the protons and neutrons, so you should remember how to do that. Since calcium's number 20, it has 20 protons. Since 40 minus 20 is another 20, I have 20 neutrons. But now I have a charge to deal with, right? If there was no charge on this calcium, I would assume that there were also 20 electrons to balance out my 20 protons. But since there is a charge, since that calcium is going to have a +2 charge, right, which would go top right, I need to make sure that I have 2 more positives than negatives. If I have 20 protons, I'm going to have 18 electrons to go with them. Right, so I would have you do this sulfur example on the right, and you still could do it if you just pause for a second and see if you can work ahead and get the correct answers. That's a great idea. But I'm going to walk through that with you here real quick, just in case you're not sure how to do this still. So again, sulfur 32. I gave you the 32, you just write it down. You look at the periodic table, sulfur happens to be number 16 on the periodic table. So that means protons, neutrons, electrons. Right, sulfur is going to have 16 protons because that was the point of looking up that atomic number. If you subtract 32 and 16, you're going to get 16. So there are 16 neutrons as well. And then finally, since there's a charge again, you have to focus on that. I don't have 16 electrons. I should have 2 more negatives than positives, which means that I'm going to need an 18 here. I'm going to need 18 electrons to go with those 16 protons. There is actually kind of a trick with that. If you want, in order to come up with that answer, just like you subtract the 40 and 20 to get 20 neutrons for calcium, you can just do the opposite of what that sign says. So my calcium charge was a +2. You can actually, since it said +2, subtract 2 from your protons, and that would give you the appropriate number of electrons. Whereas over here with the sulfur, it was a -2, so you can add 2 to your protons, and that would give you an appropriate number of electrons. So you can use that little trick if you'd like to. Just do the opposite of what that charge says, add when it says subtract, subtract when it says add, and that should give you the number of electrons. But you have to be careful when using tricks like that. Make sure you also think about the logic, right? At the end of the day, if I saw 20 protons and 18 electrons for that calcium, I would know that that has a positive charge and that it's a +2 because there's 2 more protons than electrons. Don't forget to use logic to check these answers every time. Covalent bonding. Last step to this, last slide here, is a bond formed when atoms share electrons. So this is going to be a little bit different than that ionic bonding, although I'm going to use the same ideas, the same kind of concepts. Right? The difference being now, right, I might have 2 nonmetals that are working together to achieve that octet rule. So a good example would be a hydrogen and an oxygen. Right? And actually it's going to be 2 hydrogens and 1 oxygen that make this work out at the end of the day, right? Oxygen wants to gain 2 electrons to be stable. It would end up with a -2 charge if it was going to be an ion. But since there are no metals around for this oxygen to steal electrons from, only these 2 hydrogens that also would like to gain electrons to satisfy their octet rule. Hydrogen's a little weird, by the way. Since there's only 2 electrons total in that first shell, hydrogen's perfectly happy to have 2. It just doesn't want to have the 1, right? But hydrogen and oxygen do completely different things. Instead of one losing, the other one gaining, they're actually going to share electrons, right, which I can represent with connecting dots here. Right, there's a pair of electrons that's shared between those 2 atoms. This bond that I'm making between this hydrogen and this oxygen is essentially a shared orbital between those 2 atoms, where both of those electrons, one from the hydrogen, one from the oxygen, are going to orbit both atoms really, really quickly, but they're going to hold those 2 atoms together. They're going to tether those 2 atoms together so that you have a covalent bond between the 2. Right? So our molecule definition, sorry if I wrote on top of it with that hydrogen, is when you have 2 or more atoms held together by a covalent bond. So you have to have that shared pair of electrons in a covalent bond. And a good example, like I just gave you, is a water molecule, right? But there are lots of different molecules. That carbon dioxide we talked about before, there are actually double bonds between 2 oxygens and a central carbon. Right? Or you could have something even more complicated like a glucose molecule that would look a little crazy, right? Because it has lots of carbons. Every point in this ring is a carbon except for the oxygen that's already shown. But I would also have bonds to oxygens that are bonded to hydrogens. This happens to be a very complex molecule that we'll discuss again later in this chapter. So it's a big molecule. It has way more than just 1 or 2 or 3 or 4 bonds. There are many bonds holding that thing together. So molecules can get more complex than those ionic compounds can. Right? Those ionic compounds exist in some kind of ratio. Remember I told you before that magnesium chloride would have a different ratio because magnesium ends up being a +2, and you need to have 2 negative chlorides to go with that +2 magnesium, right? And there's actually 2 ionic bonds in that compound, in that situation. But it's the same deal. Chlorine atoms lost electrons. That magnesium, or excuse me, I did that backwards. The magnesium loses 2 electrons, and those 2 chlorine atoms gain those electrons to make those ions to begin with. Alright, so that should be good. You just need to work on worksheets that your sub has for you, and I'll see you tomorrow.